Okay, welcome everyone. Today we are doing lesson 4.7, which is modeling and solving problems with quadratic functions. So we've already spent a lot of time in this chapter studying quadratic functions and how the graphs look, but we haven't spent a lot of time doing word problems and applications. So that's what today's lesson is all about. So just at the top here, we have just some tips when we're doing word problems. So I'm going to be referring to these as we do our examples today. First one is we always need to answer the questions within the context of the problem. So provide a full sentence and always include correct units. Second thing is that if a diagram or graph is not already provided for you in the question, you need to include one and you need to label it. And finally, if the question does not provide variables, like for example, X and Y, we need to define our own variables for the problem, and I'll show you how that looks. Okay. All right, so the first type of question that we're going to be seeing here is when we are trying to minimize or maximize a certain quantity. So here's a typical example. It's a classic sort of fence question. It says a person has 300 meters of fencing to enclose a rectangular garden. I'm just going to underline as I read here. One side of the garden is along their house, so it does not need fencing. What are the dimensions of the largest possible garden? So this is a realistic question, right? If you want to build a fence around your garden, you want to build one that's going to create the biggest garden possible. So let's draw a diagram here. So this would be including point number 2 here. We're going to draw a labeled diagram and we're going to identify some of the variables for this problem. So I'm going to draw my rectangle. I'll draw a nice rectangle using pre-made shape here. Okay, and I'm going to also just indicate that, actually I'll move that up. We're going to indicate that, oh, we can't do that. Okay, let's say this is the house. And so we won't need to have a fence along this side of the garden. So in the middle here, we have our garden. You can draw little flowers if you want to, not necessary. And let's label the length and the width here. So let's call this the length of the garden. And let's call this the width. Okay, so when we define our variables, what I mean. So typically, we don't want to be writing the word length and the word width out every single time we're going to use them in our equation. So we want to use letters or symbols to represent these measurements. So let's just choose X and Y. You can choose W and L as well. I just typically don't like to use L just because it looks a lot like a 1 sometimes in students' work. So I prefer using X and Y. So I'm going to say, let X be the width of the garden. So it's important to define your variables because every student might choose a different letter. So when the teacher or whoever's reading your work looks at it, they can understand what your work means because it's going to look different for everybody. And let Y be the length of the garden. You can use little quotations to mean. So our width is going to be X and our length is going to be Y. Okay, so what we know already from this problem is that we only have 300 meters fencing to work with. So, and we want to have fencing along these three highlighted zones here. We don't need fencing along the house. So our two X's, our two widths and our lengths better add up to 300 meters. So what we know from what the question says is that 2 X's and 1 Y length has to add up to 300 meters. 2 X's because there are 2 widths that we need to put fencing on. Okay. And what do we want to maximize? So this is a maximizing problem. We want to maximize the area of the garden, the amount of space it takes up. What we want to maximize area. And area is length times width, so it would be X times Y in this case. Okay, So now that you've got your variables, what you know and what you want to maximize, the next thing to do is rearrange this what we know equation in order to write it our area equation with one variable. So I'll show you what I mean here. So we're going to rearrange this to solve for y. So we're just going to move the 2x to the other side of the equation. So it's going to look like this, 300 minus 2x. Okay, it's the same equation, just rearranged. And we're going to substitute this into the area equation that we had before. So we're going to take out y and put in 300 minus 2x. Those are equal quantities, so we should be able to do that while maintaining the equation. Okay, so we're going to substitute to the area equation. So whenever you're doing a max-min problem, it's going to be the same structure every time. So we're always going to make this substitution. So our area equation is going to become x times 300 minus 2x. Notice I put a bracket around that entire thing I substituted because this x needs to be multiplied to all of that. Okay, so finally we do have an equation A for the area, which is written like this, 300 minus 2x. And we want to find the maximum of that. This is a quadratic function, and actually it's already in factored form. And we can find the intercepts of this function. So this is a quadratic function. In factored form already. So the intercepts would be at x equals 0 and at x equals 150, whatever would make that bracket equal to 0. So, we also know that this function is going to be a downward facing graph because when you expand it out, the x squared term is going to be negative. So I'll put plus downward facing graph. We'll just draw a little sketch of our graph here for the area of our function. So we would have an x-intercept at 0 and an x-intercept at 150, and it would be a downward facing graph. So this would be x, this would be area. Okay, so we're looking for what dimensions we should use to maximize the area, find the maximum possible area and what x value that would correspond with. It would actually be right in the middle here, and that would be the vertex of the graph would represent the maximum area. So the vertex, remember, is halfway between the x values. So halfway between 0 and 150 is 75. You can add them up if you want and divide by 2. And the area when x equals 75 would be, we could plug it into our area equation, 75 times 300 minus 2 times 75, which would equal, well, the question doesn't even, yes, plug it in. Oh, sorry, I forgot to grab a calculator. I'll just now quickly. 75 minus 300 minus 2 times 75. The maximum area would be 11,250. And this is meters, yes, meters squared. Okay. But what we're really looking for is the dimensions. The question asks for what dimensions. So that means what's the x and the y? What are the length and width of the garden that are going to maximize the area? We've already found the x dimension, the width of our garden. We need to find the y value of our garden. So we found the maximum point now. We just need to kind of finalize our answer. So the width is 75 meters. That's the x. To find the y, the length, we're going to use the equation we came up with for y. That's highlighted in yellow there. 300 minus 2 times 75. And that would give us 150. So the dimensions that would maximize the area of this garden would be 75 meters for the width and 150 meters for the length. So we're going to answer that in a complete sentence. The dimensions that maximize the area of the garden are 75 meters, and I'll put in brackets, that's the width as labeled in our diagram, and 150 meters, and I'll put in brackets, length. Okay. Any other size you make your garden, you're going to have a smaller garden than that. That would be the best possible way to make your garden. Okay. So again, let's just kind of review what we did. We drew a diagram, we defined our variables, we wrote down what we knew, which is we needed to use 300 meters of fencing. And then we wrote down an equation for what we want to maximize. We found the vertex, the peak, the maximum point on the graph, and then we stated our final answer. Okay, so that's an example of a maximum minimum problem. The other type of question we might see is a problem where we're trying to model a shape or a certain object with a quadratic equation. We've seen a couple of these throughout the chapter, but I just wanted to go over one more time. So this one says, a bridge spans a horizontal distance of 40 meters and it has a parabolic arch. 10 meters from the end of the bridge, the arch is 6 meters high. Determine an equation for the function that models the shape and how high is the arch at the center of the bridge. So what you want to do straight off the bat when you have a question like this is draw a graph. So set up an axes, X and Y axes, and draw the actual bridge. And I always like to draw it so that the edges of the bridge are sitting right at the origin and another point along the x-axis. Could be a bridge, could be another object, but always kind of set it up so it's in the positive part of the coordinate grid. Okay, and let's label some points on a graph. So we know it goes through 0, 0, and we know the bridge spans 40 meters. So we also know that 40, 0 is going to be on our graph. So we do know the two x-intercepts. And we also know that there's a point here that when we are 10 meters from the end of the bridge is 6 meters high. So that means that the point 10 for x, 6 for y is on the graph. So we have a little bit of information here that we can go off of. I'm going to start in factored form. Whenever you are given the x-intercepts, it's a good idea to start in factored form. So we know that we don't know the a value for this equation, but we do know that the two brackets would be x minus 0 and x minus 40. In fact, you don't need to really subtract by 0 if you don't want to, so you can simplify this to a times x minus 40. Okay, and what we haven't used yet is this point here that I'm highlighting in blue, so we're going to use that now to solve for the a. Okay, so I'm going to plunk the x and y values from that point into my equation and solve for a. Substitute 10, 6 into equation and solve for a. Okay, so it looks like this. 6 equals a times 10, and then in brackets 10 minus 40. So again, I just substituted the 10s for the x's and the 6 for the y. And I'm going to multiply these two numbers now. So we get a times, so 10 times 10 minus 40 is negative 300. And I will use algebra to solve for a by dividing both sides by negative 300. And that gives me a is negative 0.02. You can also write it as a fraction. I'll put or a equals negative So 0.02 is the same as 1 over 50. So it's up to you whether you want to leave it as a decimal or a fraction. Either way is fine, at the same number. Okay, so our equation that models the bridge, our final answer, that models the bridge is y equals negative 0.02 x minus 40. Okay. Or you can write it like this, y equals negative 1 over 50 x minus 40. You don't actually need the bracket around the x because brackets are used in math to contain more than one term. And so since we're not containing more than one term there, I'm just going to erase the brackets for clarity's sake. Okay, you could put dots there for multiplication or leave them out. Up to you. Okay, that's it. So that's a modeling question. So far we've done a maximum problem and a modeling question where we're modeling the shape of a real life object. Third example is another max-min problem, but it's a little bit specific, the strategy we use to solve this one. So I'm going to go through it. So there's a couple of questions in your workbook as well that have this kind of structure. And so you can use the same strategy we use here for those. So it says, every week a takeout restaurant sells approximately 200 chicken tacos for $150 each. Okay, sorry, 2,000, not 200. Through market research, the restaurant manager determines that for every $10 increase in price, she's going to sell less tacos, 100 fewer tacos. That makes sense. If you increase your price, less people will want to buy it. It says, what is the price of the taco that will maximize revenue? So the word revenue, if you don't know it, it just means the amount of money they're getting from these tacos. So you want to maximize your revenue. That makes sense. If you're a business, you want to make the most money possible. And then the second question is, what is the maximum revenue? Okay, to do these price questions where we want to maximize revenue, what we want to do is create a table to try and get a pattern going to write an equation. And you always want to set up your table in the same way, right? So we're going to do, it's going to be 4 columns. Price increases. We're going to do price. We're going to do numbers sold. And we're going to do revenue. Okay, which is what we want to maximize. Okay, so if I have no price increases, if I just keep everything the same, the price we're selling at right now is $1.50, and we're selling 200 tacos. And the way you calculate the revenue is, 2,000. The way you calculate the revenue is you just go $1.50 for every taco times 2,000 tacos. So $1.50 times 2,000. Actually, you know what? I'll use a dot for multiplication so it doesn't look like an X. 2,000. And you get $3,000 in revenue. So each week, this takeout restaurant is earning $3,000 for their taco sales. Now, if we make one price increase, that means we're going to add, it says in the question that when you increase by 10 cents, so we're going to add one price increase. So 0.10 is 10 cents times 1. So it'll be $1.60 in total. It says we're going to sell 100 fewer, so 100 times 1 less. So it would be 1,900 tacos. And our revenue will be 160. So we're earning more, but we are selling less, 1,900. So if you calculate that, it's $3,040. So actually it's better. It's better to increase the price to $1.60. Let's see what happens if we change the price to $1.70. So I would take my price and I would add 2 price increases. So 10 cents times 2. And what would happen to the number sold? It would decrease by 100 times 2. So it decreased by 200. And my revenue would be $1.70 times 1,800, which ends up being 3,060. So it's actually even better. We want to increase it to $1.70. We're going to earn more money. But what's the best amount of increases to have? Okay. So let's say I have X price increase. So I'm going to go dot, 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 X. What's the pattern here? The price would be $1.50 plus 10 cents times X, okay? And the number sold would be 200 minus 100 times X. And the revenue would be these two numbers multiplied together. So the revenue would be 150 plus 0.1X. The number sold would be 200 minus 100X, and that would be my revenue. Now we want to maximize this. Okay, so let's find the maximum of that function. So we want to find maximum of R of X equals, so this is a revenue function here. It tells you X is the number of price increases, and the function will spit out what the revenue will be, depending on how many price increases you want to make. So we want to find the maximum of this. So this already is in factored form. So if we're in factored form, it's simple to get the x-intercept, or I shouldn't say simple, but it's the benefit of factored form is that you can find the x-intercepts. So there's two x-intercepts, one making each bracket equal to 0. So x-intercepts, one is going to be where 1.5 plus 0.1x equals 0. Solving that one first. Let's move the 150 to the other side. I get 0.1x equals negative 150. Divide by 0.1. Get x equals negative 15. That's one x-intercept. The other x-intercept is at where 200 minus 100x equals 0. Same idea, we're going to move the 200 to the other side. I'll have negative 100x equals negative 200, and I'll divide by negative 100. Get x equals 2. So that's the other x-intercept, or sorry, 20. Yeah, I always put 2,000. I put 200 this whole question. It should be 2,000. My bad. I went and fixed all of it. So all these 200 should be 2,000. I don't know why I keep thinking 200. Okay, so I've got two x-intercepts now. And we know this is downward shaped graph because when you multiply this out, the x squared term is going to be negative. So we have, we can find the maximum really easily. Well, not really easily. Stop saying that. But the graph is going to look like this. The x-intercepts are at 20 and negative 15. And the maximum here is going to be right in between the two. So to figure out where this maximum point is, we can add up the x-intercepts and divide by 2. We find the average of the two. So 20 plus negative 15 divided by 2 is 2.5. And so 2.5 or 2.5 price increases will be the best possible revenue. So we want to actually, and then, so that's part A, what price of a taco will maximize revenue? So the price is right here. So if X is 2.5, part A, I'm running out of space here a little bit, but we're going to have 150 plus 0.10 times 2.5. And that's going to give me $1.75. So $1.75 is the best possible price that we should set for these tacos. It's going to maximize our revenue. And for part B, I'm going to use the yellow equation to calculate the revenue. So this is the price because it was in the price column. Yeah. And this is the revenue. So I'm going to use my 2.5 that I found, plug it in, 2,000 minus 100 times 2.5, and I get a maximum revenue of $3,062.50. That is my maximum revenue. So every week, if I set my tacos to $1.75, I'm going to earn $3,062.50, and that's the best possible way I can do it. If I increase the price anymore, my revenue is going to go down because I get less people buying them. If I lower the price anymore, I'm going to get more people to buy them, but I'm going to earn less. So that's the best possible revenue I can make. Okay, so every time you do a maximum problem with prices, you want to set it up in this exact way, making a table and then setting your price increases to X to get a pattern there. Okay, so that's the end of the lesson. I'm going to stop the recording.